Welcome everyone to our channel Mathematics Pathshala. This is a problem of CSIR NET September 2022 Mathematical Sciences. The question ID is 395. This is a problem of abstract algebra from part C. See the question first. Which of the following statements are necessarily true regarding a group G of order 2022? The four options are given here. So see first, let us first start to counter one by one that which one is not true. So for this, first see option 4. It says that G has only two normal subgroups. So in question there is given only G is a group of order 2022 and option 4 says that G has only two normal subgroups. So if we take G equal to that cyclic group of order 2022, that is J 2022. So 2022 has more than 3 divisors. In fact 2 is a divisor, 3 is a divisor, in fact also 6 is a divisor. So there are since G is abelian, there are subgroups of all such orders and all subgroups are normal subgroups. So G has at least 3 normal subgroups and there are another subgroup, say subgroups of order 1011, that is also normal. So G has more than 2 normal subgroups. So option 4 is not true in general. Okay. Now see option 2. So this set is a normal subgroup of G. So we know that the order of x equal to order of G inverse. This is very easy to prove. This is a very well known standard and easy result, so we are not going to prove this. So to prove this, H is a normal subgroup. Take one element x belongs to G and take one element G belongs to H. Now we have to uh, prove that uh, okay, let us use the notation with the help of this. So it will be confusing if we choose x from this and this. Okay, so we are taking one element G belongs to okay, let me write this changing some, then it will not be confusing. uh, if we take any element, if you take any element x belongs to G and G belongs to H, now we have to prove that x inverse belongs to H or not. Now we have this order of G equal to order of x inverse. This is a well known standard and also easy result. So now uh, this we have taken G belongs to H, so order of G is odd. So our order of G is odd, and also by this result order of G equal to order of x inverse is also odd. So this element x inverse belongs to H. So we have taken x belongs to G and G belongs to H, and we have x inverse belongs to H. So H is a normal subgroup of G, whatever the order of G. So this is the option 2 is true in general. Okay. Now let us come option 1 and option 3. So first we are in option 1. So for option 1, see, we are given that G be an element of G such that order of G is odd, and SG is given a permutation on G, that is a bijective map from G to G defined by SGX equal to GX. X belongs to G. Now it says that Sg is an even permutation. So let us now calculate. See here, G is a group of order 2022 that can be written in 2 into 1011, that is also written 2 into 3 into 3, and then it is also 3, the 21, so it is 7. So 2 into 3 into 337. So since G is a element of odd order, now the odd, we must have order of G divides order of G, that is 2022, and odd divisor of 22 are, odd divisors are 3 and 337. There are no other odd divisors of 2022. So we have order of G must be either 3 or 337. So first let us suppose that order of G equal to 3. Now see, we can write this group G explicitly like this. Say x0 x1 dot dot x 2021, where x0 is identity element, and where we are writing this in such way that sgxi is equal to gxi, and we denote this element by xi plus 1. So in this way we can write the elements of G in such a way. Now see, just calculate this. SGX0, this is GX0 and this is our X1. SGX1, this is our GX1, which is equal to X2, and our SGX2, this is equal to GX2 is actually our X3, and also this X3 is actually our, this x3 is our gx2 what we have just written, and x2 is also our gx1, so this is g square x1, and x1 is also our gx0, so this is g cube x0, and order of G equal to 3 we have suppose in this case, so it is e, so it is x0. So what we are getting, x0 goes to x1, x1 goes to x2, x2 goes to x0. So if we write this permutation in this cycle form, then we have this Sg equal to here x0, x1, x2, x3 dot dot x2021, then x0 goes to x1, x1 goes to x2, x2 goes to x3, sorry, x3, x2 goes to x0 by our definition, x2 goes to x0, and similarly by our the element we have defined, we have x3 goes to again x4, and so on. This x4 will go to x5 and x5 will go to again x3 and so on. So this is in cycle form, we have x0, x1, x2. This is a cycle of length 3, and similarly all such we have a cycle of length 3 and in this way. So there are some, there is a product of some disjoint cycles of length 3. and each cycle is of length 3, and since there are 2022 elements, so there are 2022 by 3 equal to 674 number of disjoint cycles of length 3, and from each of these cycles we have the product of two transpositions. So this is actually x0 x2 x0 x1. So there are total this 674 into 2. For each 3 cycle we have 2 transpositions, so there are total 674 into 2, that is 1348 number of transpositions. So there are even number of transpositions, so this SG is an even permutation. And exactly in the similar case, when we suppose that order of G equal to another odd divisor, that is 337, exactly in similar manner we will get Sg in such a form that Sg equal to here x0 x1 dot dot x336, and similarly there are other some cycles of length 337. So there will be total 2022 by 337, so 6 cycles each of length 337, and for this cycle of length 337 we have 338 number transpositions. So 338 into 6, we will have 2024 number of transpositions, that is a even number. So SG will be an even permutation. So each of these case, if order of G is odd, we will have SG is an even permutation. Okay, so our option 1 is correct option. Option 1 is correct option. Now we will calculate the option 3. It says that G has a normal subgroup of index 337. We will show that this option is not true in general, and we will now show for the dihedral group of order 2022, and we will show that this group, that is D1011 Dn n equal to 1011, a group of order 2 into 1011, that is 2022, has no normal subgroup of index 337. See first. See first, if G has a normal subgroup of index normal subgroup of index 337, then our say the subgroup is say H, then we have G index H equal to 337, and since this is a normal subgroup, that is G by H, the quotient group is of order 337, so H is a subgroup of order of G by order of this 337, that is actually 6. So that means G has a normal subgroup of order 6. So now see here, H is a normal subgroup of order 6, and we are considering the group G equal to actually D1011, and that will be generated by two elements, say A and B, where order of A is equal to 1011, that is n here, and one zero one one, order of B equal to 2, and BA equal to A inverse B. The definition for a dihedral group, this is. Now See, there are elements, G contains elements of order these three types: a to the power I type, a square up to a to the power 10, then one element is b, and other elements are of the form a to the power I b. These are the three types of elements of order in G. So H contains only three type of elements. So first let us suppose that what type of a to the power I for which I belongs to may belongs to H. So if some a to the power I belongs to H, then what happened? Then this order of a to the power I, that is actually by a standard result in group theory, that will be order of a, that is 1011, by GCD this I comma 1011, this is. And also, since this is an element of H and order of H equal to 6, so order of a to the power I divides 6, so this divides 6. So we have, so the divisor of 6 are 1, 2, 3 and 6. But this number, this 1011 by something, cannot be an even number. This clearly cannot be an even number, because if it is even number, then 1011 equal to some even number into this GCD 1011. So left side is odd and right side is even, so it cannot be true. So this must be an odd number. So the only possibility is either 1 or 3. There are two possibilities. And also this cannot be 1. This cannot be 1 uh, because if it is 1, then this I must be 1011, which cannot be true, because a to the power 1011 is actually E. So that also belongs to H. So the non-trivial case is only, this is 3. So now let us calculate. If it is 3, then what is maybe the values of I? So this 1011 by GCD I comma 1011 equal to 3 implies this 3 into GCD I comma 1011 equal to 1011. So it implies that, easy to verify, that I may be either 337 or 674. There are no other option for I. So only a to the power 337, a to the power I, a to the power 674, and also E, these three elements can belong to this normal subgroup H. Now we calculate that if this B can be in H, or a to the power I B can be in H or not. So first, suppose that B belongs to H. Suppose B belongs to H. Then, since H is normal, we have A, B, A inverse belongs to H. And it is easy to calculate that this A, B, A inverse is actually our A square B, that belongs to H. And since B belongs to H, we have A square B composition B inverse, that will also belong to H. That is, we have A square belongs to H, which is a contradiction, because if H contains some a to the power I, then I must be only this 337 and 674. No other element. No other element of type a to the power I. So this B cannot belong to H. Now see if a to the power I belongs to H or not. So If possible, suppose a to the power I belongs to H for some I, then what happened? Then since also H is normal, we have this a to the power I B, A inverse belongs to H. That means easy calculation shows that a to the power I plus 2B belongs to H. And also we have from this that a to the power IB belongs to H, and from this say uh, okay, then it implies that if for some I a to the power I belongs to H, then all a to the power I plus 2B belongs to H, then H will contain more than 6 elements. So it cannot be true. It cannot be true, and it said there are so many other ways to contradict the fact this a to the power I plus 2B belongs to H, because we can take this a to the power IB inverse with a to the power I plus 2B belongs to H, and calculating we can arrive at a contradiction that some a to the power I will belong to H where I is not of the form 337, I is not 337 or 674. So this cannot happen. So also a to the power IB cannot belong to H. So this a to the power IB type elements cannot belong to H, and also B cannot belongs to H. So only H contains the elements of a to the power I where I is 337 and 674. So this uh, H may be at most a group of order 3, a subgroup of order 3. So this order of H is 6, which is a contradiction because there are no since H cannot contain elements more than 3. At most 3 elements can be in H. So this is a contradiction. So this group, this dihedral group D1011 of order 2022 cannot have a subgroup, cannot have a normal subgroup of order 6, that is a normal subgroup of index 337. So option 3 is not true in general. So option 1 and option 2 are true in general, and 3 and 4 are not the correct option. This is the solution of this problem.